Hello and welcome back to Differential Equations section 3.7 on electrical circuits. So we talked about mechanical engineering a lot, right, so far, and we haven't dealt with electrical. And about 90% of electrical engineering is mathematics. So knowing how to set up these systems obviously is very, very important. Now, we are going to take a look at some very rudimentary stuff that from the perspective of electrical engineering is considered as a biggest laughing joke of the entire science there, but we have to know the basics in order to do anything bigger than that. So what we are going to do today for electrical circuits of alternating currents is technically 1 plus 1 equals 2. That's the level. Now, you might not perceive it that way because, again, this would be the first time maybe you're dealing with electrical, but this is literally 1 plus 1 equals 2 of electrical engineering. Now, where do we start? First, we have to learn the components because most of you are not familiar with these components. Now, the mechanical components you are familiar with, with the wheel, with the spring, pendulum, or like all these things, they're constantly around you. You can see them. Now, in electrical circuits, unless you played with this, as a kid and took stuff apart and took interest in what they are, you don't know. So we have to learn. So we're going to take this basic electrical circuit, which we would call an RC circuit, or whatever, and I'm just going to go through each component and tell you what they are and what they do in what you would say real life, because over here is a fake life. So this is an electrical circuit, and you can see that the circuit is like a one continuous loop in this case, and you have your switch over here, which can be switched on and switched off. When you switch it on, when you close it, right, then the electrical current should flow through the circuit, and each one of these components does a different thing. So we're going to start with E over here, and that one will be called like a voltage source, okay? Or a current source. So this is the equivalent of the plug in a wall. I don't want to say the battery because this is not direct currents. These are alternating currents, which means that the polarity of a plus and minus that you have on a battery switches according to the frequency at which the circuit is oscillating at. So you know that 50 hertz or 60 hertz, depending which country you're in, that's the frequency, meaning that the plus and minus sign flips 50 or 60 times per second in order to deliver, right, the electricity. So that current flow perceived through the wire, which is one electron bumping into another one, is switching the direction of motion of those electrons 50 or 60 times per second. So you have the voltage source. Now, to understand the voltage versus current, current is perceived as a flow of electrons through the wire. Actually, the electrons are not flowing. They're transferring energy, bumping into the next electron bumps the next one, and so on. Not all of the materials have those free electrons around to bump. So some materials would conduct electricity, meaning will have free electrons to move, and others like plastic will not, and they will be insulators like rubber as well, and so on. So when you have the flow of electricity like that, every time you say a flow, you would like to have a high and a low spot. Think of flow of water. right, which flows downhill. So the uphill is the higher point than the low point at the bottom of the hill, so the water will flow down the hill. You can also contribute that to potential energy, right? And then that potential energy turns into kinetic energy of motion, and the water flows down to the lower level. Now, voltage is actually the difference of potential which is created between the 2 points, so the current can flow from one end to the next. So literally exactly the same as water. You are providing a high potential place and a low potential place, and then there is a flow between them. The same thing the wind, guys. You have a difference in atmospheric pressure. You have a high pressure on one side, low pressure on the other, and then there is a flow of air immediately created between the two, and you call that wind. So you have the same behavior between the wind, high pressure, low pressure. You have the water, high altitude, low altitude. You have the current through the wire with a high and a low as well. And that high and low is created by voltage, which is called also voltage potential, right? Which creates opportunity for the current to flow through the wire. Now you have these. So that's the voltage source that creates the potential. That's the E. Then you have the switch, right, on and off, which allows for the flow. And if you disconnect, then there is the infinite gap there, and electrons can't jump over. And then you have the three components. We call this RLC circuit, RLC, because it has these three components. R is the resistor, and that's actually your spender. So that could be your cell phone charger, could be a light bulb, could be a computer you plugged in, a fridge you plugged in. So that's a spender, something that would use up the power produced. Now, power is voltage times current. We're not going into that, but if you want to know these kind of things, you will have the current going through the wire, and then the voltage provided. They together give you the power. So now you have the resistor, and that's the one that spends. And then you have these L and C. L is the inductor, and C is the capacitor. And they are energy storage devices, technically. So if you can use the voltage source, so let's say a DC one, direct current, charge the capacitor, and then you disconnect the battery, and that capacitor is charged. It has charge in it, just like a battery would have a charge. And then if you connect something to it, it will release that charge and make that device work for a very short period of time, because capacitors discharge almost instantaneously. Not instantaneously, but almost. They discharge very quickly, and they give up all of their energy. And they're also used for other purposes, but this is not a circuits class, so I'm not going to go into the smoothing properties of it and all of the other things that it can do. It's a storage element. It stores energy as charge. Now, inductor is also another storage element, but it stores energy in terms of magnetic field. So when you put the current through the inductor, the coil will create a magnetic field, and then you can use that energy, right, because the magnetic field can be converted back into electric field, right, for alternating currents. That doesn't happen for the direct, only for alternating, because you have to have this switch in direction in order for coils to work. So if you are interested more to learn about these circuits, I can give you a little bit more. At least I can teach you how your chargers work. Let's say that would be the simplest thing to figure out how you get to plug in a charger into AC outlet and get a DC voltage on the other side to charge your phone. We can go over those things. Those of you interested, you will join office hours and you can ask those questions. Now, what's happening here is that this source of voltage will give certain voltage, and then each one of the components connected here in what we say series, right? When the tail of the one is connected to the head of the other, so they are all in a series. There will be a continuous flow of electricity that would constantly, change its direction, left, right, left, right, left, right, whatever, or counterclockwise, clockwise, counterclockwise, clockwise, whichever way you want to think. Each one of these components, except the switch, will have what we call the voltage drop, meaning that some of the voltage that it's provided by the source will be used here, other part would be used there, most of it would be always used here, and when you add all of these, they would equal all of the electricity provided. So think about it the same way. What did I say earlier? Water. If you have a water source that is providing water to 3 cleaning stations, let's say the car cleaners or whatever, then when the water is on, then the total amount of water produced by the source can be used between the 3 stations where the people can wash their cars. Okay, so that's the same idea. You cannot use more than what is supplied, right? And everything that you put in a system will be split between these. Now they're not split evenly. They are split according to the intensity, size, whatever of the components in question. Now you can also have circuits that have some of these components missing and so on. So we'll see what that means. Now let's talk about these voltage drops. So I already said that you are going to have the voltage drop, let's call it VC, VL, and VR, and then those 3 together will give you the total voltage, which is E. So VL plus whatever VR. I was thinking to go in order, but it doesn't matter. VL, VR, and then we have a VC is equal to E. Now, what we said before is, so the sum of all voltages, right, is going to be given, will be the same as the voltage that it's produced. And what we are going to have here is the voltage drops are measured. Now, this is going to be the science of, the physics of it. You have L times the change in current in time plus resistance times the current plus 1 over capacitance times the charge is going to be equal to the voltage produced for the entire circuit. Now, I mentioned current twice. What is current? I told you already that the current is flow of electrons through the wire, right? But current, the I, right, as a function of time, is the change of charge in time. So think of current as the water flow. It's the change of amount of water from one place to another, the change in air pressure, right, which creates the wind. Wind would be that current. So water flow, wind, or current. Now, when you're talking about the current, it's the change of charge in time. And now you get to plug this one for each current inside these equations, right? And what you get is L d dt of I is dq dt plus R times dq dt plus 1 over c of just q, there's no I there, equals et. Now we recognize this as a second derivative. So to write this simply, it's L q double prime plus rq prime plus 1 over c q equals et. And you go, hello, right? Hello, second order constant coefficients, because inductance will be given, like, let's say 5 henries. Henry is the unit to measure inductance. Resistance will be, I don't know, 50 ohms. Ohm is the unit to measure resistance. And then C, which is capacitance, will be given as, I don't know, 10 microfarads. Farad is the unit that measures the capacitance. And it's farad as a unit is a huge number, so all of your devices will be using nano, pico, and microfarads. You are not going to find millifarads anywhere, right? The entire planet doesn't even have up to a farad of unit. Anyway, so of capacitance. So when you take a look at this, you have your second order differential equation, right, in terms of second order differential equation in terms of charge. Now, generally, we don't care about charge. We want to care about the current. So there is a little trick that we can use to transform this into a current equation. Please recall that dq dt is current. So if I differentiate this equation in respect to time one more time, I will get L q triple prime plus rq double prime plus 1 over c q prime equal e prime of t. All I did is I added another derivative throughout because I just differentiated one more time. Now, what is the LQ triple prime? It's L d dt d dt dq dt plus R d dt dq dt plus 1 over c dq dt equals e prime of t. And each dq dt now is current I, which gives us, now written in red, the equation that we want. L I double prime plus R I prime plus 1 over c I equals e prime of t. And this is the equation that you would use to solve one loop of a circuit. And now that circuit can drop any of the components, can have all three, and you go from there. Now, if you have two loops, multiple loops, and so on, then obviously the issue is, right, you will have coupled differential equations that make a system of differential equations that would get you to do these things. I just have to run real quick and make sure that, as I said, with the homeschooling, I just need to make sure that my daughter is in her class for 12:30, and then we are going to, actually, what you can do now, by the time I go and check that, you can solve the initial problem where resistance is given as 30 ohms, inductance is given as 10 henries, capacitance is given as 0.02 farads, and your ET is given as 50 sine 2t volts. So plug those numbers in and you can solve the, I'll be right back, you can solve the differential equation. This is going to be the standard equation we did with undetermined coefficients. Nothing new there when you plug in numbers. I'll be right back. Okay, so standard stuff, like always before. We'll plug in 10 I double prime. This is your X double prime from before, or Y double prime, whatever. Now it's just I. Plus 30 I prime plus 1 over 0.02 I equals, and you need now derivative of this. Derivative sign is cosine, so it's 100 cosine 2t. Usually this is where the grade dies, right? Because you forget to take the derivative of the source. So in order for you to have the equation in using current, which is what we want, you have to have a derivative there. If you want to solve the equation through charge, which we never need, then it's just E. Anyway, 1 divided by, so 1 divided by 0.02 is going to be 50, right? So we are going to have, so this number over here is 50. And then we can divide through by 10 and just have, right, so divide everywhere by 10 and have just I double prime plus 3I prime plus 5I equals to 10 cosine 2t. And as you can see, we are down to the basic, coefficient, constant coefficient equation, which we know how to solve using either undetermined coefficients or variation of parameters. So now I'm going to, I'm not going to solve this because we know how to solve this. I want to go back and talk more about the circuits and stuff, but this is the way, right? So now we solve using was it 3.5 undetermined coefficients? Yes, 3.5. So it's just a basic standard calculation. So what you are going to have here is this part here and this part here. So the one on the left is called transient current, known as ITR, right? And on the other one is steady periodic current. So ISP. And together they create the solution for the current. This is the same, guys, you used to have. C and XP, and now you have these things. It's the same thing, so that's the solution. And as I said, you're solving this exactly the same way as you were solving it before. We don't learn new mathematics here. We are just placing this in the new framework, in a framework of these circuits. So now you are going to have the same idea if you remember your equation that we did for mechanical, right? Where you had those constant coefficients given by those constant coefficients given by equations. So now we can come up with the same equations here, which will give us the now instead of having M, C, and MC and K, we're going to have R, L, and C. So the equation is the same equation, it's just that it's written in the values of electrical engineering. So it's going to be E0, that's the voltage, and then you have your cosine omega t minus alpha, and then you're going to have your R squared, that's the resistance, plus omega L minus 1 over omega C, everything squared, and this is going to be the equation. Now the phase angle alpha is going to be the tangent of B over A, so R omega RC divided by 1 minus LC omega squared. You can literally go and replace, you will say M equals L, right? So those of you that want to have any chance of ever becoming electrical engineer and actually being anything remotely close to it, your job is to rederive these equations by following what I did for mechanical, but simply say M is now going to be L, the C is now going to be R. Calculations are the same, and the good old K is now 1 over C. So absolutely same calculation as before. Absolutely no difference in any of that stuff. And that's it. That's all it is. So you just put these equations in. Put these variables, well, parameters, L, R, and 1 over C, and follow the same steps as in mechanical, and you will come up with these equations. Now, this is your solution. You can see here. This is the solution from the left-hand side. It has those that phase shift alpha. in it. Alpha is given what it is in terms of RC and L. If you change any one of them, obviously things change for the circuit, and you go from there. And yeah, that's technically it. Now there are equations for direct current which we are not considering here because direct currents do not have the wave-like behavior. Remember, direct current is just a flow in one direction, so there is no oscillation that would make these things work. You need oscillation in order to make the inductor create magnetic field, so on. So the AC circuits and DC circuits are obviously different. Most of the components obviously are the same, but there are some things that would not work the same way just because of the type of the voltage source that you are using. So your home outlets and everything that you run not on batteries, right, that you're running from the from outlets, that's all alternating currents, which changes its polarity, and all of those components, you can have transformers and so on. You cannot transform the voltage the same way using DC when you have your when you have a DC circuits, right? Because the AC circuits are the one that can have the coils and inductors, and then put the voltage up and put the voltage down. So, you know, the calculations for these problems again are this simple. Again, you're going to have electrical resonance. Sometimes you have to be very careful when you are putting online the power plant, like you have a new, let's say, generator that's going to generate electricity, or you put solar panels that convert very inefficiently, convert the solar energy into electrical energy, and I believe they're only 45% efficient, and they obviously take a lot of space, and they don't work when it's dark, and it's just terrible solution for alternative energy. But I don't know, people think it's good. It's actually not. If your IQ is bigger than 7, you know it's not a good solution, but whatever. But if you, let's say, put the solar panels and you want to integrate that in a home grid, you can't just connect the wires and be done, right? Because the electricity provided by the panels and electricity provided by the grid have to be in phase. Otherwise, they can cancel each other out. They can create the resonance, for instance, and obviously the resonance is going to make a couple of small explosions along the way in your electrical boxes, and you know, where the fuses are and so on. So all of these things that you had in mechanical, the same way you would destroy a mechanical system, you can destroy electrical system with resonance, and you know, because they oscillate as well. Now, those things do not happen with the DC current, but the DC current is really deadly. That's a problem. DC current is really dangerous. You do not play with you know, voltages bigger than 12, 24 volts. Maybe I wouldn't play with the 24 volts, but you do not play with voltages bigger than, you know, because they can be deadly. Actually, electrical chairs are made with DC currents. AC current is a way safer option. Human body should not have any lasting effects up to 60 volts. 110 is going to give you a little bit shock, but it's not going to do any damage, you know, big damage, where, you know, 110 of DC, you just become a liquid at that point. Just think that all of that gold plating and silver plating and everything is done with the DC, right, current. So I think it's called electrolysis or something like that. Because it changes the chemical structure. So being hit by the DC is chemically changing, where because electricity flows only one way, where the AC current keeps changing electricity. Also, a lot of people don't know that we are impacted and harmed by electricity because we work on electricity. Our brain produces electrical impulses that travel through our nervous system. And I believe it was a 16 or a couple of microvolts, very, very small currents flow through our nervous system. And then when you want to move a muscle, what the brain does is it sends the electrical signal through your nervous system. And then when the electricity is introduced to the muscle contracts and you're able to move fingers and right. And then your brain learns over time, right? Because you're a baby for some time without any motor skills and so on, you learn how to use your limbs. Technically, your brain learns how to run your body through electricity. Now you have also electricity that runs your heart and so on. So when you get hit with the external electrical source, it resets the electricity that makes you work as a human. Now, clearly, if you have millivolts, right, in your body produced by a brain, and then you get hit by 110, right, obviously, it's going to override all of the brain impulses, and then you can't open, like if you grab a wire, right, you can't open the fist because obviously the electricity is making all of your muscles contract. You can't open the arm. The brain is sending signals to let go, but it's sending millivolts, and over there it's 1,000 times more or 10,000 times more. So obviously that's where the issue is. So yeah, we are very, very sophisticated robots, right? We work on the battery, which is our brain, and you feed that brain, right? The food that we eat is converted into nutrients that go into the brain, and brain is able to generate that electricity to run the rest of our body, including the heart and all the organs, not just the muscles. So now I hope you understand how important this is. If you want to do any serious medical research, any serious neurological research on the brain and stuff, if you want to develop electrical circuits, you want to develop new computers, cell phones, processors, new cars, finally, right, electric cars, and all of these kind of things. This is the very basic, because all I did, and this is why it's 1 + 1 = 2. All we had is a circuit with 3 components in it with a source, right? And that's nowhere near the billion of components that are in a processor today. Billion. Yes, 1 billion. Not a million, but a billion, right? So think about the networks and the wiring and the systems that have to be put together, right? And things you have to compute through in order to get through all of these things. So that's it. The setup is clear with this equation. You have your inductor, resistor, and capacitance. You know where to plug them as values. And then don't forget to take the derivative on the right-hand side for your source. And then you just solve the equation the same way you learned in 3.5, nothing new there. Undetermined coefficients, variational parameters, whatever, magic, right? And then the solution can be given in terms of this expression here. This is now SP, right? We are not counting the transient solution, which is the R equation, right? The R squared plus 3R plus 5. That one will give you I transient, and then I transient, which is just equal to 0. I transient plus this solution will give you the the total solution for the current through that one loop. Now you can have multiple loops, which is what the circuits class is all about. Where in circuits class, if you're taking circuits at the college, right, at RV, you are going to see systems of differential equations of the second order, which you are supposed to solve. We are going to see those systems in our class. We could do a word problem involving electrical or mechanical with those systems. But you need to understand that all we did here is the very basic circuit, which is one loop only, which means one equation, and you have those three components that produce those three terms. And that's it. That's it. So that's going to be our 3-7 for today. Next class on Wednesday, we have the endpoint problems and the eigenvalues. We're going to deal with that for you know, a little bit. A lot of application obviously for this, but this is where the higher end mathematics starts with advanced differential equations and so on. So we're just going to take a look at what those things are and finish chapter 3, and then we'll push on next week. So I will see you all in 2 days. Oh, and also the exams will be posted by the time of the next class. So if they are not posted tomorrow afternoon sometime, they will be posted on Wednesday morning. I don't like to drag that for too long.